Hey all, in this video we're going to take a look at some limit theorems. So we're going to get into section 4.2 and we're going to jump right into theorem 4.2.1. So if we have two different sequences, S sub n and T sub n, right, so we have our two different sequences there. If they are both convergent sequences with S sub n converging to S and T sub n converging to T, then the limit of S sub n plus T sub n is simply S plus T. Right? So that is the limit of the sum of the sequences is equal to the sum of the limits of each of the individual sequences, the values that they converge to. Right. The second thing that we have is if we multiply every term in the sequence by some value k, then that limit is going to be k times the limit of the sequence, or what that sequence converges to. And similarly, if we add k to every single value in the sequence, then it is going to simply add k to the value that it's converging to. Our third thing is if we have take the product of every term, a term-by-term product of the two sequences S sub n and T sub n. When we take the limit there, it is going to again be the product of the limits. So whatever they're converging to, they're converging to that product. And a similar thing happens when we divide them, right? So the limit of the quotient of the two sequences is the quotient of the limits, provided that we don't have 0 in the denominator, and that for any of those individual terms, or for with a value that it's converging to. All right, so let's prove the first one, the first piece of that. We're going to prove that the value that the sum of those two things, of those two sequences, that limit is the sum of the limits of the two sequences. So let's let S sub n converge to S, and T sub n converge to T. Note that if we were to look at the absolute value of S sub n plus T sub n minus S plus T, that is exactly the same as writing, so we could rewrite the stuff inside, and so we could put the S stuff together and the T stuff together. So we'll make that quick observation, and not only do we have that, then our triangle inequality would tell us then that S sub n minus S plus T sub n minus T, that should be less than or equal to the sum of the two individual pieces. Yeah. So that's kind of just a first initial observation that we'll make, right? And so given epsilon greater than 0, since we have S sub n converges to S, we know there exists a natural number n such that whenever little n is bigger than big N, or is at least big N, greater than or equal to big N, this implies that we must have S sub n minus S is less than epsilon over 2. Right, and this is the same kind of trick that we've done before. So in the past, right, it's really less than epsilon for every choice of epsilon. So just take half of epsilon, and that should still be true there. And so this is a nice, nifty little trick that will help us kind of get some stuff that we would like to show up maybe a little bit later on. All right, and similarly, since T sub n converges to T, there exists another value. Let's call this one N2. And let's go back up here. Let's call that first one N1. So there exists an N2 such that N greater than N2 implies T sub n minus T is less than epsilon over 2. Right, and so we go through that, and so if we put those, after making those observations, when we put those together with that note from above, would then tell us that we have the absolute value of S sub n plus T sub n minus S plus T. That's going to have to be less than the value of epsilon. I don't want to highlight that. I was trying to choose the eraser. I'm sorry, guys. So that absolute value of S sub n plus T sub n, it should be minus S plus T, should be less than epsilon over 2 plus epsilon over 2 for every single choice of epsilon. And so therefore the limit of S sub n plus T sub n is in fact equal to S plus T, which is what was to be proved. And so part B is part of your homework. And that's it for this video. We'll look at some more stuff dealing with limits in our next video.